just recollecting. Okay, so what I told you on the first class, did you remember? I was keep on talking about the kinetic theory of gases and how this thermodynamics works, right? Thermo is nothing but a heat and kinetic theory of gases. See, first topic will be kinetic theory of gases and zeroth law and first law of thermodynamics, reversible and irreversible process and Carnot engine, right? These are the topics we have already discussed the basics of the fundamentals of the theory of the gases, how this thermodynamics works, how what is the reversible and irreversible process takes place, how this Carnot engine works. I have given you the complete information and the basics of the thermodynamics, right? In the first class, we have discussed so much, the topics of the 4 units we have discussed. We will go little micro level of these topics and we will discuss about the kinetic theory of the gases according to your syllabus. Okay. So in this kinetic theory of gases, you have the introduction, assumptions of the kinetic theory of gases, mean free path, graphical representation of velocity distribution of gases, Maxwell's law of distributions of molecular speed, transport phenomena, viscosity of gases, define of viscosity, equation for coefficient of viscosity, thermal conductivity of gases, diffusion of gases, summary model. Okay, let's start with the objectives. Okay, so before let others also join. In the meanwhile, we will see the topic wise what are it is being given and all. Okay. So objectives, after going through this unit, you will be able to define mean free path, explain the distributions of molecular speed of gas, describe the transport phenomena of the gases. Further, with the help of the transport phenomena, you will be able to describe viscosity, thermal conductivity, and diffusion. Okay, let us read and see what is given about this introduction. Once other two people or another people, if they join, I'll directly explain the topics and concept what is being given in this kinetic theory of gases. Okay, Sapa? Oh, sorry. The
Okay, ma'am.
name?
Yeah,
I
it's a
guess.
fun, ma'am.
Yeah, Safa, right? So let
Yes.
us see the introductions. Okay, with the advancement of experimental equipment or techniques, it became possible to achieve low temperatures and high pressures. Okay, normally, if we take about the current, so it flows only in one direction, right? When coming to the kinetic theory of gases, what it does, the molecules, that might be air molecules, water molecules, gas molecules, atoms, whatever it is there, what it does not flow in equilibrium. It is a non-equilibrium. What is equilibrium? You have to know. Equilibrium is nothing but which flows in one direction at a time is nothing but a equilibrium. Okay, which does not flow in equilibrium is nothing but a non-equilibrium. So, for example, if I'm talking about a kinetic theory of gases, the gases have the molecules which will be colliding with one molecule to the another molecule. Let me explain you with my video so then you can understand more. You can see me? Is that clear?
Yeah, yes, ma'am.
Okay. So what happens in the kinetic theory of gases, the molecules will be combining and colliding with one molecule to the another molecule in a zigzag model. Okay, in a zigzag. It does not flow in equilibrium. Equilibrium is nothing but which flows in one direction continuously. For example, if I'm taking a current which has a positive half cycle and a negative half cycle, right? So the positive half cycle which will be flowing continuously means it will take only positive half cycles and we are getting a lights, fans, whatever the gadgets, whatever the equipments we are using right now, everything is a direct. Okay. So that means the current which is flowing is a equilibrium. Equally, it will be transmitting from one level to the another level continuously. The passing of the flow of the charges is equilibrium. But coming to the gaseous, the molecules, water molecules, air molecules, what are the gaseous, whatever we take now, that will be not in a equilibrium. It will be colliding with one molecule to the another molecule. The collision takes place. It attaches to one molecule to the or other molecule. Clear? So we are speaking or communicating about the gaseous state, how this gaseous state collide each other and how the elasticity forms. That is about this topic and the introduction. So here what happens? Temperature can be increased or decreased. 1 second. So what happens? This the way the collision takes place and the gaseous molecules are going to be formed. Whatever wave you take, it will be in a frequency. The natural frequency is nothing but everything will be flowing in a sine wave. That might be air molecule, water molecule, light, whatever the frequency, whatever the air which is flowing, everything will be in a sine wave. It's a natural God's created the wave that is always a wave will be in a sine wave. Clear? Okay, so here why I'm talking all this and explaining you much about this gaseous molecules is because these molecules where the temperature, pressure, volume is going to be involved. Okay, when we talk about the current, which will be having working as a on and off. If you on the fan, on the switch will be acting as a on and off mode. There will be no rising of the temperature or decreasing of the temperature. When we talk about the gaseous molecules, you can use the pressure, temperature, and volume, where you can increase the pressure, temperature, and volume. It can be increased or it can be decreased. Okay, here there is no need to make necessary changes in theory to explain the behavior of perfect gases. Kinetic theory of gases was developed by Maxwell and Clausius and others. Gases are made up of molecules. The molecules are considered to be rigid, perfectly elastic, and identical in all aspects. Molecules move in all directions with all possible speeds. Rigid means it will be in the same position. It does not move from one place to another place. That is what is about the meaning of the rigid. During their motion, molecules collide with each other and with the walls of the vessels in which they are kept. The intermolecular force between the molecules are neglected. There will be no loss of kinetic energy during collisions are perfectly elastic. Only change in momentum occurs. The molecules thus exert pressure on the walls between two successive collisions. A molecule moves in a straight line. The distance is called the free path of the molecule between two collisions. The average distance traveled by a molecule will be in its mean free path. Molecule takes more time to cover mean free path than the time spent in a collision, which is negligible. Okay. Next is assumptions of kinetic theory of gases. What can be first what they have done? They have this is all the assumptions. This is the way this is the going to happen. This is all about the theory. They have assumed and they have written it and then they have done the experimental way. Okay. So assumptions of kinetic theory of gases. So what will be the assumptions of the kinetic theory of gases? Let us see that also. Hello?
Yes, ma'am.
Yeah. What are the assumptions? What they have assumed? 1 second. Nobody is joining still. It is 12:20. Okay. So let us see the assumptions of the kinetic theory of. I'm going to assume about. See here, before going to little more further of this kinetic theory of gases, we have isothermal process and adiabatic process. What is isothermal? Where you can change the pressure and volume and temperature will be constant. In adiabatic process, what happens? Pressure, temperature and volume, all the three can be varied. According to the temperature, it can vary. Clear? So we are going to discuss next is nothing but your isothermal process and adiabatic process. So let us see what is this assumptions of kinetic theory of gases. Let us consider the following. before actually writing the assumptions. Assumptions means I am thinking. It may happen in this way. It may work in this way. Is nothing but assuming or assumptions. So in that way, they have, because of this, the gaseous states, how it is colliding, how it is working, how it is going, and how it is transferring from mean free path is means nothing but how it is freely moving from one place to another place. Okay, that is what is about the theory of, that's why the theory and the introduction of the gaseous state, kinetic theory of gases. So gases will be there, which will be readily formed, but while you are putting some energy to that, then only the state of that can be utilized, right? So, for example, uh, what I can give you the best example, we are using the gas cylinders, right? At our home appliances. So that gas, if you are using only, that is converting into heat energy, right? Then only we are able to cook the rice or whatever the utilities we are utilizing to burn the water, to steam the water or the cook the food. That is converted into heat energy. You are understanding? I'm trying to give you the best example how these gas molecules are going to be used in our regular usage. Okay. So in this such a way, so many gaseous molecules are going to be collide and it will be ready. How we are going to utilize that molecules is there in our hands. So, whatever the gaseous states, how it is going to be formed, it will be forming in a zigzag way. It will be colliding with one molecule to the another molecule. You need to assume. You need to imagine. Okay, through our eyes, we can't see that molecules. Clear? So we need to assume the physics all the time. It will be in assumptions. Then we are going to add the mathematical part, and then we are going to calculate. That will be applied, and we are going to be used. Okay. See, for example, if I'm taking the phone, it's a phone, I'm charging it, right? I'm charging it, and the radiation or the current, whatever it is being charged, it will be utilized. But I can't reverse that energy to get back. You are able to follow? Hello? Hello? Hello?
Yes, ma'am. I'm following you.
Okay, okay. Because I'm going to the deeper level and I'm explaining. I don't know
Mm.
that if you people don't, if you don't respond, I will be in confusion.
Mm.
Okay. Okay. So let us see the assumptions of the kinetic theory of gases. So whenever the explanation part takes place, no, then I'll explain uh, through the video call. If anything to be read by from this theory, let us see this. Okay. Assumptions of the kinetic theory of the gases. So let us consider the following before actually writing the assumptions. So what are that? The pressure exerted by the gas according to the kinetic theory is given by, which is being given by. This is the equation. P, pressure is P is equals to 1 by 3 mn V square bar by V, that equals to equation 1.1, where V is the volume of the container, N is nothing but number of molecules, each M is nothing but the mass. Okay, each of the mass, and Mn is equals to capital M, that is mass of the gas, that is M by V is the density of a rho of a gas, rho of the gas. So V square bar is the mean square speed of the molecules. So ultimately what we need to find the speed of the molecule. So how the molecule is connecting to one molecule to the another molecule, how it is colliding, how it is taking place, how it is transferring from one molecule to the another molecule. Ultimately, we understood the theory. Oh, this is the concept. It is going to collide with one molecule to the another molecule. All the molecules will be combining and forming a gaseous state. We know that. So I want to find it in a mathematical way because I want to use that molecules as a gaseous state. So I want to find out. So what I'm doing, that formula, I'm using it as where I'm taking the volume, molecules and number of molecules and the mass of that and the gas of that and the density of that and finding the mean square speed of that molecule. I want to find ultimately how the speed is going to take place and with that speed how it is going to utilize the gas molecules. Okay. Example, you can take it as a cylinder. The cylinder where you have the uh, gas molecules where it can be utilized. When you are owning the, what is this? Stove, immediately the gas molecules are ready and it is flame. If you lighten, it will be, you are getting the flame, right? So the speed of the molecule, I just want to find. So for that, to calculate that, to utilize that, what we can do, we will take it in a small quantity first. Then we are going to use it and how this going to be worked. Then we are going to be used in a bulk. So to find out that, we are going to find the mean square speed of the molecules. That is V square bar is equals to V1 square plus V2 square plus so on. Vn square by n. We can write equation 1 is 1.1 as where we can write pressure is equals to 2 by 3, 1 by 2. Rho is nothing but the density of the gas by V square is nothing but the square mean square speed of the molecules. Ultimately, we are going to find the speed of the molecule. That equals to 2 by 3 kinetic energy of the molecule. Okay, that will be 1.3, the equation. Then coming to this equation 1.3 shows that the pressure is two-thirds of the total translational kinetic energy. Kinetic energy is nothing but where we are applying that to convert into an external energy. Okay. So of the molecules per unit volume. This kinetic energy of translatory molecules of an ideal gas is directly proportional to its absolute temperature. So on this assumption, the concept of temperature was introduced into the kinetic theory of this basis. We can show that as half mv squared bar equals to 3 by 2 k of t. So from this equation we can here k is nothing but Boltzmann's constant and k is equals to r by n where r is the being universal gas constant that is 8.314 joule mole Kelvin and n is Avogadro's number. Here hence the mean kinetic energy of translation per molecule of a perfect gas is nothing but 3 by 2 k of t. K into T. If we put T equals 0 in the equation, that it becomes V square bar equals to 0. So we can infer that the absolute temperature and the temperature at which the molecule cease to move. This is not true, as the molecules do not have some energy known as 0 point. Energy according to quantum mechanics, so here they have given the explanation how this kinetic theory of the gaseous molecule is going to work as a dynamical system of the number of the particles. So the total intermolecules energy of the system will be distributed equally among its various degrees of freedom on the basis of the law of equation of energy. Okay, so you can read this step by step how this is going to work. And coming to the Maxwell's, so the Maxwell ultimately what he could find is that the number of molecules in a certain volume of a gas is very large. The velocity of these molecules can be from 0 to very high value. So the density will be same at every part of the volume of the gas at all times. Okay, fine. Explanation and the how this velocity can be used in the molecules continuously in equilibrium and a fixed temperature. The number of molecules having certain range of velocity is constant. So here I've explained that molecule is three mutually perpendicular directions as considered to be independent for each other. So, okay, this they have explained the step by step, given the explanation how it is going to work. So, next will be mean free path. So, mean free path means what? How it is moving freely from one place to another place. That is about mean free path. So, just read these steps, these 5 points, where you can understand how these molecules are going to be utilized, how this velocity, pressure, temperature, everything can be distributed equally, how this is going to be converted. So next phase will be the Maxwell's distribution law, where you can find the complete picture of how the speed can be transformed, how it can be utilized. So the number of molecules in some velocity range can be determined. Means the molecules, how the molecules see. This is about where what we are talking is nothing but we can't see through our eyes. So you need to imagine, you have to imagine how these molecules are colliding with each other. So all the gas molecules will be colliding with each other and it will be ready. So once it should be utilized, then it will be ready to come out. The pressure and the volume is helping to come out and that can be utilized. Example, you can take a best example is here. At home, we can take a best example is our cylinders. So all the molecules in the cylinder, what happens? It will be ready to come out because the pressure and volume is applied to that and that is coming out as a gas. With that gas, if we are firing it, it can be utilized and how again, so that is another topic where these gas molecules are converting into heat energy. Because of the heat energy, the vessel is starting heated. If you have in that vessel, if you're pouring some water, again that water is going to be heated up from top to bottom. Okay, again, a systematic process is also happening continuously. Continuously takes place. So, the Maxwell's have proved a continuous speed of the molecules, how this molecule collide and how it can be taken place. See, for example, if we are taking a cylinder, the gas molecules, whatever it is coming out, and when it is full cylinder is full and you can the gas will be coming out with a proper pressure and you can utilize it. When it is coming, the gaseous states are going to be utilized, and if it is coming down, so it takes time to travel and to come out. So if the cylinder is empty, it is going to be um the full gas is going to be utilized, and if it is low, so what happens, your flames will be less. We have observed, right? It is used in our daily appliances. So how this mean free path, so the gas molecules which are low down, it takes time to travel from low to high level. So that is what we are going to talk about, the mean free path, how this is going to be pass freely. Okay, so far, others
Yes, ma'am.
others also joined. I'm happy for others too. They have joined. Rajani is also joined and Tikri. Okay. So others, if you have doubts till now, you can communicate with me. Because this topic already I've started in the last class and I've explained how it works and how it is going to be taken place. If you read once this material, it is so easy, so clear. If you read once also, you'll understand. But you need to understand the topic and content of that, why we are reading, how it is going to be utilized, why this much of macro level of explanation is given to this topic. So this is completely you need to imagine while I'm explaining. If you imagine, you will understand so clearly. The thing is that little imagination part you have to imagine and you have to understand. So if you have any doubts, You can stop me and you can ask me. If not, I'll be continuously keep on teaching you. No doubts, Tapa and others?
No, ma'am.
No? Clear?
Yes.
See, I'm just reading because these topics are well known to me, but I'm just going to glance the topics what they have given. Okay, coming to the mean free path, as I told you, see, lambda is nothing but always a wavelength. Lambda is nothing but a wavelength where it can be traveled. You can see, so the wave, all the way, always it will be whatever the molecules or current, whatever you take, as I told you, it is a natural God's given frequency. Air molecule also flows in a wave. Sound wave will be wave, it will be in a wave. Light also travels in a wave. Okay. If you take electric field also flows in a wave. Magnetic field also will be in a wave. This gas molecules also flows in a wave. Everything, whatever you take in the natural uh, creation, everything is in a frequency. The sound which is coming from my voice, okay, which is going to your ears, also will be in a wave. Everything will be transmitted in a wave. Water molecules also will be flowing in a wave. The molecule to molecule which is going to be added is also in a wave. All the time we talk about a wave. We deal with a wave, we talk about a wave, we read about a wave, and whatever the calculation part we do it is also in a wave. This is what about your physics. Completely what we talk, however whatever the calculation part we do, ultimately everything is in a wave. Okay. So, these molecules of gas move continuously with large velocities according to kinetic theory of gases. They collide with each other. Okay, definitely. I told you the molecules. See, if I'm talking in your semester one, you might be um learned about the vector and the scalar, how the vector will moving from one place to another place. All the time it will be in a arrow. Okay, but here it does not flow like an arrow. It will be colliding with one molecule to the another molecule. All the scalar and vector field will be in a proper equilibrium. This will be non-equilibrium. It will be colliding in a zigzag model. The current, whatever it flows, it will be in one direction. But this will not be in one direction. However, the molecules are going to be colliding each other. The output, whatever it is coming out, it will be in a wave, but the collision takes place in a zigzag mode. So now we are talking about a mean free path, means when it is coming out as a gas, how it is moving. Okay, so at each collision, the speed and direction of the molecules changes. The molecules moves in a straight line between two successive collisions. This distance is called free path. Let A, B, C, D be the free paths. The average distance is lambda traveled between two collisions. So I'm just going to connect and I'm just talking about two collisions. Two collisions is nothing but colliding with one molecule to the another molecule. So if I'm able to find for one molecule to the another molecule, I can find for n number of molecules, right? So I want to see the distance from one molecule to another molecule. Let me yeah, I just want to share the means. I just want to tell you how this is collision takes place. Okay. Safa, Rajani, are you with me? You're
Yes,
listening?
ma'am.
Okay. See, I'm talking about the molecules, right? All the time I'm talking about the molecules. In your first sem and second sem, you might be understood how this vector, where you have both magnitude as well as direction. We have studied about it will be having, even if you take in a curl also, it will be moving in one direction. Even if it is having a divergence also, it will be moving in a proper arrow model. Okay, here the molecule, I am taking one molecule to the another molecule. So the molecule to molecule which is colliding, right? Until I'm talking about collision means which is going and hitting another molecule. Collision means hitting. So the one molecule to the another molecule, if I'm able to find the distance between one molecule to the another molecule. So if I could find for one molecule to the another molecule distance, I can find for the n number of collisions taking place. So that is the average distance lambda traveled between two collisions. I'm talking about two collisions, one to one and one to another collision. That I can take from this molecule to this molecule or this molecule to that molecule. So here I'm taking the distance, average distance as lambda A, B, C, D plus so on by n, whereas n is the number of the collisions suffered by the molecules and lambda is called as mean free path. So mean free path is nothing but after taking the collisions, how it is moving, how it is traveling is nothing but a mean free path. Clear? We can define mean free path as the average distance traveled by a molecule between two successive collisions. Successive collisions means, see, all the molecules, which is the active molecule, will be immediately going and colliding with each molecule. It might be in a zigzag model. It does not flow, does not collide. See, molecules are there. From one molecule is here, another molecule is here. It directly go and collide with that molecule. It does not see that molecule should be a straightforward or a backward. Wherever the molecule is being placed, it will be going and colliding with each and other molecule. Clear?
Yes.
Okay. So here you can see your progress. Space is given below for writing your answers. Compare your answers with one given at the end of this unit. Define mean free path. You can write it down with your own words by reading all this, and you can write down by your own. Okay. So this you can read it. Now you understood what is a mean free path, how the collision takes place. So how the distance can be calculated from one molecule to the another molecule, how the collision is taking place. So I'm going to find the, see here diagram is given A and B, and this we are taking here as two molecules, the distance A and C. The molecule under consideration will collide with all those molecules whose center lies within a distance D. This is the distance D from its center, figure A. We may describe the collision by taking the diameter of the molecule under consideration be 2D. Okay, all other molecules as point mass, particles as P. Just a diagram they have given how this can be taken as a consideration. So let us consider a gas consisting molecules of point mass particles. Let us now think that a molecules of equivalent diameter 2D is moving with a velocity v through the gas considered. Let us assume the molecule under consideration as a point mass particle of the gas exert no force on each other. There is no force. Okay, so automatically one molecule is there, another molecule will be colliding with another molecule. There is no force applied to collide. Okay, so if I just want to find in such a way, see, I have taken a container, the molecules are placed here. Okay, so how these molecules are going to be collide with each and another molecule. In a time t, the moving molecule travels a cylinder of length. Okay, so let us see this diagram, everybody. So the moving molecule travels a cylinder of length. I have taken a cylinder. Molecules are filled over here. Okay, of a length v of t. Here I am taking the length v of t. The molecules are placed over inside this. So here how the additionals of this time t in the moving molecules will collide all the molecules whose center lies within the cylinder, whose axis is the line of motion of its center and radius d as shown in the figure. See here, the molecules are there. So these molecules are colliding with each other molecule. I am going to find the distance. Okay. The radius. How this radius is going to take place. If I am able to find for this small cylinder, I can find for n number of molecules which are going to be colliding. So to find out that, to simplify it, to utilize it, I'm just taking a small example and small container of the cylinder, and I am able to calculate the molecule to molecule. So ultimately whatever it is coming out will be in a gaseous state. That is later part. Okay, but inside the molecules, how it is been colliding and how it is passing. See, this molecule is there. This might be colliding with this, that. It will be in a zigzag. But ultimately, the wave which is coming out will be a wave. Okay. So here I'm going to find the volume of the cylinder, number of the molecules per unit, and the number of molecules in the cylinder. So the average time between two successive collisions means, see, successive collisions means this is colliding with this is colliding with this, or this can be collide with this, or this can be collide with this, and this. It will be in a zigzag model. It will not flow or not collide like a, tell me, hello.
In a straight line, one
Yeah,
direction.
perfect. See, it does not. It might be collide with any zigzag model. It does not flow in a straight line. Okay. So in that way, we are able to find the average time between two successive collisions. We are talking, we are reading, or we are communicating at the basic of the basic, completely basic, how they have invented, how this collision is taking place. With this collision, the invention, the theory or practicality or research work done with so many efforts, and these are the basics. Every time we need to, it will be there forever. These are the basics of the physics. After so many decades also, we have to read this. Our next generation also will be reading the basics of this. Another topics may be added to this, but this will be never destroyed. Clear? So the average distance between two successive collisions means you know that now. So the distance traveled by molecule in 1 second by the total number of collisions made per second. So it is see, I'm talking about the collision. I'm talking about the distance. I'm talking about the motion of the molecule. So I am finding step by step. What I'm going to find? The distance traveled by molecule in 1 second. So how much in 1 second, how the distance is, because molecules are there, no? Are there. But what it is happening? It is colliding with each other and it is traveling. I am able to find the distance, I am able to find the collision, I am able to find the complete picture of the successive collisions. I'm talking about two successive collisions means I can find for n number of successive collisions. So that thing, but the average distance between two successive collisions is nothing but distance traveled by molecule in 1 second by total number of collisions made per second. So this is the formula V by pi t square Vn is equals to 1 by pi t square n. That is nothing but mean free path. That is the distance is equals to 1 by pi t square n. If m is the mass of the molecules, then mn is equals to rho. We know rho is nothing but the density of the gas, and lambda is nothing but the distance. M is equals to mass by pi d square by rho. Rho is nothing but density, d is nothing but the distance. So here we know that m by pi d square is constant and lambda is proportional to 1 by rho. So this is about the mean free path, how the density of the gas can be calculated, and how we can derive the equation for the mean free path, and how we can consider this into reality. Next comes to the Maxwell's, how from this distribution of the formula or the distribution of the molecules, the Maxwell, he could find the speed of the molecular speed. So with this distance, that is lambda is equals to 1 by root 2 pi d square n. From this, where we can find the next is graphical representation of velocity and the distribution of the gases. How this is going to be distributed. So Maxwell's Boltzmann distribution. So here you can find the speed and the molecules. How does it can travel in a speed, and it can be shown in a curve as the number of the molecules which is given. Speed range is obtained by the area under the curve shown by the shaded area. So let us see this graphical representation. Here you can find the peak. Okay, most probable speed is nothing but V of P. This we call it as most probable speed V of P. And this is the average speed. Okay, and this is the root mean square speed. VRMS, we call it as root mean square speed. This will be the molecules, how it has been traveling. See, all the time everything will be in a wave. I'm talking about a molecule, right? Again, what we are finding? It is in a wave. The molecular one, each molecule also how it is going to be traveling the speed and average speed. I'm just talking, but everything is in a wave. See, this curve is also in a wave. As I told you in the starting, everything will be in a wave. Whatever the molecule which will be colliding with another molecule, again it will be in this way. Again it will be in that way. Clear? Concept you are able to follow?
Yes, ma'am.
See, step by step, I'm not reading this theory part. I'm trying to explain you because we need to cover more topics. So this is the explanation of the graphical representation of the molecule. As I told you, everything will be in a wave. So here we are able to find the speed of the molecule, how this is been traveling. So if I'm talking about one molecule, I can talk about n number of molecules. So here area under graph equals total, which is not equal to the molecule. So here you can see cold gas, how it is traveling, room temperature gas and hot gas. The graphical representation of the molecule differs, but ultimately it will be in a wave. Got my point? Okay, so here you can see the different gases, room temperature gas, cold gas and hot gas, how it is been traveling. It takes time to travel. The cold molecule will be having a high peak of the molecule, and again it takes, because the cooling effect will be much. The molecule of that will be touching the high level of the peak and it takes time to come down. But hot wave will be very easy to travel. The radiation. Summer, we feel so much of radiation, right? The heat energy will be transmitted so easily through the sun and we get dehydrated. Okay, so you can read that and you can understand what is the explanation. So simple, nothing much complicated. Next is your Maxwell's law of distributions of molecular speed. So he can find the speed of the molecule. You want to find Maxwell have derived his molecular speed with a assumption and with a calculation. He could prove this Maxwell's law is always live. Always. Okay. See here, I'm going to explain this more little depth, how he could find the equation. So, which is hmm. Okay. See, Maxwell's I'll discuss in the next class. Before that, I just want to talk about transport phenomena, or how it can be transport, how it can be to this. Viscosity of the gas. Let's check it.
Ma'am, this will be our last class.
What, ma?
This will be our last class, I guess, according to the
Yeah,
timetable, right?
yeah. This we have discussed, no?
No, I'm
This.
saying this class, I guess it will be a last one,
Why?
according to the timetable.
Why next Sunday you don't have class?
No, 11th was the last day today.
How many classes you'll get for the semester?
5 Sundays we got for
Hmm.
online classes.
Okay, that's it. For
Yeah.
semester only five.
Yes, ma'am.
That's it. Only five classes.
Mm.
So shall I take little more then?
Yes, ma'am.
Hmm? Then I will not go step by step. I will try to explain you the concept that.
Okay.
Okay, better. Okay, so
Yes.
if you read, you will understand. See, I what my ultimate trying to give you the input is to understand. See, even if you read this theory part, you will understand. But the thing is that you need to understand the concept. If you understand the basic of the concept, if you read, you'll understand. The derivation part also will be easy. So let me see the ultimate kinetic theory of gases and what is this? Thermodynamics is completely about how you can convert, let me tell you, see how you can convert heat energy to cold, cold energy to heat. See, for example, if I'm taking uh, water is boiled, right? I can make it heated up and I can even make it cool. Again, I can make it cool and I can make it heat, right? This process can be happened. See, I'm giving the current to the refrigerator and I'm getting a cooling effect. Yes or no? ACs.
Yes.
I'm supplying the current to that and I'm getting a cooling effect. So the reversible and irreversible process is there. That is what we are talking. Next topic will be that only. Reversible and irreversible process. So reversible process means if it is going in one direction, I can turn that into another direction. That is reversible. Which is irreversible is nothing but which I cannot do that. See, reversible process means heat to cold, cold to heat, I can do. That is reversible. हाँ कि नहीं? Yes or no?
Yeah.
Yeah, I can do that changes to the reversible process. But irreversible process is nothing but I'm taking the current. I'm utilizing the light, fan, charging my mobile. See, I'm just taking the energy, but I can't again give it back, no? I can give it back. I can take it, but I can't give it back. That means nothing but irreversible process, reversed, which cannot be reversed, right?
Mm.
So I'm having, see, the heat energy will be produced from the heat energy I can't reach, cannot be charged, you know. But in reversible process, I can make it cool, I can make it heat. The process can be done in both vice versa. But in the irreversible process cannot be done. So coming to the transport phenomena, which is going to be transport the energy or the molecules, whatever, which can be helping to move from one place to another place. Transport phenomena. Phenomena is nothing but we are talking about the molecules. So how it is going to transport the energy of the gas molecules. Okay, how it can be turn up or how this collision takes place with that collision, how it can be movement from one energy to the another energy. Okay, so that is about the transport phenomena and Maxwell's distribution law. Let me tell you, this is very, very, very important. You will get it for definitely for essay question. Okay, next class, when you have exams, ma'am?
From 5th March, theory
5th March.
exams are starting. And
So
from tomorrow
then
onwards, practical class exams are there.
practical classes are there.
Exams, ma'am, from tomorrow.
Practical. Okay, fine. So no, no worries. Till March you have time, no? March 5th, right?
Yes.
Another two classes, I'll take it and then finish it off. So
Okay,
one
ma'am.
Sunday we lost it because we got some New Year or festival holiday. One
Yes.
last 1 week, last week I was not well. I could not take. Don't worry, I'll complete your syllabus. Okay.
Okay.
No worries. I'll give you the important questions also on the
Okay.
last day, what to be read and all. So this Maxwell ultimately what he could find, I'll tell you the topic. See, there's so much of derivation part is there. So what he have done is nothing but he could find out the speed. See, this is a molecule. Okay, let me tell you. I'll just explain this part and rest of the thing you can calculate and you can write it down. Okay. See, let us consider a gas. Let us suppose the molecules are present in a velocity diagram. Let O be the origin here. O be the origin and O to X. Okay. O to Y and O to Z. Okay. As a coordinate axis, as shown in the figure, let us represent the velocity a molecule by a vector C. Okay. Where it is? Where is the C? Vector C, where for the letter, let U, where is U? Yeah, U, V, and W with the projections of this vector in X, Y, Z directions. Okay. In the element of the volume du. Okay. Du, all molecules whose velocity components lies in the range of U and U plus du, V and V plus dV. So this is the assumption. Okay, the rays which are coming out, which is being drawn is the assumption. Okay, this is a molecule. See, let me tell you. I have taken a one molecule. Okay, I want to find the molecular speed of this. So what I have taken, one molecule I have taken, I'm just calculating by taking the three directions X, Y, Z and the assumption part as U, V, W. Okay, here U, V and W, where it is representing the same X, Y, Z axis. So which is an imaginary part, I'm taking it as U plus DU and V plus DV and W plus DW. So from this, what he could find is nothing but uh, one molecule is there which is colliding with another molecule. See, I'll tell you by explanation. Yeah. Okay, listen. See, try to understand. See, I'm talking about one molecule to another molecule. It doesn't mean that one molecule will be going and hitting another molecule. I'm talking about the collision, right? So the collision, how it is taking place, how we are calculating is nothing but the wave which is being transmitting from one molecule to another molecule. It will be traveling as a wave. The energy is being transmitting means, for example, I'm talking about, let me give an example, lithium. Okay, lithium niobate oxygen is there, for example. So lithium to niobium, lithium to oxygen. It means that the energy, for example, a light wave is passed to lithium. What happens? A light is passed on any molecule or any atom or any, yes, molecule or atom or what we can call it as. Okay, let us take a molecule. So what happens? It start vibrating. What happens? It start vibrating and re-radiating because external energy is being fallen on that and started reacting. So the reaction which is taking place is nothing but we call it as radiation. All the time we talk about radiation. If we are using so much of gadgets and all, what happens? Even our body gets heated up and we get radiated. The radiation gets attracted to our body, and our body molecules, atoms, whatever it does, it cannot take more radiation. Clear? Is that clear?
Yes, ma'am.
So this one molecule to the another molecule is colliding with each other, means it is not, collision is nothing but, it does not mean that it is dashing each other. The energy is being transmitted from one energy to the another energy. That's why we are able to find the distance, how it is traveling from one molecule to the another. This Maxwell's distribution have could find explain so clearly what will be the speed of the molecule from one molecule to the another molecule. The speed of the molecule or the distance of the molecule is nothing but the wave which is transmitting from one level to the another, one molecule to the another collision, one collision to the another collision. These are the terms what we are talking about. Okay. So one molecule to the another molecule which is being traveling means nothing but it is going in a wave and hitting another molecule. Well, hitting means it is traveling in a wave because external energy is being supplied, no? External energy, that might be light wave, that might be any wave which is helping to collide with each other. So that is what this Maxwell could prove, that ultimately how the collision is taking place, what is the speed of the traveling of one molecule to the another molecule. Clear?
Yes, ma'am. So, ma'am,
Okay.
these waves are the radiations.
Yes. See, from light, what we are getting out is nothing but photons,
Yes.
right? See,
Yeah.
light is also a wave, but a glass material is being helping to release the photons. If single light is there, that will not be transmitted as a photon. The material which we are adding up as a glass material, that which is transmitting in a wave, and it is covering our room. The light is traveling as a photons in a wave, and the radiation will be there.
Mhm.
Definitely. The
Yes.
radiation from the sun, from the light, from the gadgets, whatever which the electricity which is producing out is everything in a radiation. Even our body is also having radiation, right? So that's why we get heated up, because our body is also functioning, and the heat energy, whatever we are taking it, at certain level we can absorb. If it is beyond that, what happens? We get headache, we get feeling of vomiting sensation and all. If you continuously watch TV, or continuously if you use phone, continuously if you are using your laptop or desktop, whatever, what happens? We get dehydrated because all our body water molecule absorb that radiation. It will maintain for some level. Then what happens? We get dehydrated. Why we always say, yeah, we will be dehydrated because all our body water molecules are being absorbed by the radiation. Clear?
Yes, ma'am.
Everything is, this science is related to our general appliances and general body, whatever we take. Everything, this science is so beautiful to understand. If you go little deeper level, it is everything is connected. Everything is connected. Okay. Clear? So this is
Yes.
about the Maxwell's distribution of the speed. He could find. You just derive it and you solve it. If you don't understand, in the next class we will discuss. Okay, this is about the transport phenomena and viscosity of the gases. What is viscosity? Viscosity is nothing but flowing along a horizontal surface. So how these gas molecules are traveling from X, Y, Z. Why I'm taking the X axis, Y axis, Z axis? Because which can be traveling in any axis. It can collide with X axis, Y axis, or Z axis. Right? As a current, it does not flow in only one direction. It can collide with any direction. So I am able to find for X, Y, Z directions. Okay, that is about the viscosity of the gases. See, they have taken this diagram, X-axis, Y-axis, Z-axis of the molecules, how it can be colliding with each and different axis. Okay, just go through it. You'll understand. Then finding out the coefficient of viscosity. One more. I'm just
Ma'am, can you just once define viscosity?
viscosity. Okay, let us see this. Okay, so here, okay, let's go with this topic. So ultimately, viscosity of the gases. We need to know what is viscosity. See, I was in the previous topic, I was talking about the x-axis, y-axis, and z-axis, right? So how these axes are taking place? So this axis which is helping to travel from any direction. That might be in any direction. Okay. So what is viscosity? Meaning, you just want to know the viscosity meaning. So the
Yes.
resistance can be in a liquid form or a gaseous form. Okay. That can be in a liquid or a gaseous form. So it can be in a change in a shape or portions of the relative to another. So for example, if I'm taking a water, the measuring of the fluid or the measuring of a consistency or the measuring of the lower level to the higher level. I'm just finding out. Okay, I can find the water viscosity or a thickness of the viscosity. Means nothing but measuring of the fluids is nothing but the resistance to flow. See, for example, if I'm taking a water, water can flow, no? If I make it to flow, it can flow. So I can measure that, the resistance to flow. See, if I'm taking a thick batter, for example, if I'm taking honey, example, let us take honey. It is a liquid form, but it is having a thickness.
Thick.
Yeah, the viscosity is nothing but the flowing of the resistance. That might be the resistance to flow. That might be a liquid form or it might be thick. For example, if I'm taking, as I told you, honey is a thick batter, right? It is a liquid form, but it is little thick. If I flow the water and if I flow the honey, the flowing of the water will be more than compared with the honey, right? In the
Yes.
same way, why I'm talking about this is because converting from solids to liquids, liquids to solids. All liquids all liquids cannot be see all liquids can become a solid, but all solids cannot be a liquids. For example, if I'm taking a iron, I want to make a shape of that. So what I do, I'll try to burn
Heat.
that and melt it, and I want to take that the viscosity means I want to take the flow of that fluid. Clear?
Yes.
Okay, ma?
Yes,
Understood?
ma'am.
So that is about the viscosity of the gases, how these molecules are going to be collide with each other, how this is can be formed. Enough
Mhm. Yes,
of this
ma'am. Thank you.
viscosity? Okay. Next topic. Mm, okay. Very important. Thermal conductivity of gases. Thermal is nothing but heat. Conduction is nothing but which is helping to conduct. Conduct means which is generating some heat. Thermal itself is heat. Conductivity means taking some action. Heat to be converted or it takes conduction. What to be say conducting means the heat can be conducted. Heat conductivity of gases. Conduction is nothing but which is taking the process
Travels.
to happen.
Mm.
Okay. So I've see I have taken the uh we now we are using more thermal products. See to maintain some heat. Thermal water bottles we are getting. If I'm pouring some water in that thermal bottle, what happens? Heat water I've poured. So minimum 8 hours it will be in the, maintaining the same temperature
Temperature.
in that water. Oh, the conduction taken place means it is
Mm.
going to be taken in such a way that the conduction means heat energy is produced and it will be maintained in that. So here, the molecules are supposed to be carried of heat energy. Molecules, what is happening? Carriers of heat energy. So here I'm going to consider an area A dash. They have explained how this conduction takes place, how it can be maintained, how it can be converted the heat thermal energy into a heat energy. Clear? So this conduction takes place and the energy which is being transmitted as a heat is maintained. Means for so many hours the thermal energy is maintained. 1 second. Sorry. Hello? Hello?
Yes, ma'am.
Yeah. So we are talking about thermal conductivity means thermal means heat and conductivity means which is helping to maintain that heat energy. Okay. So if I, for example, I have boiled the heat, sorry, sorry, boiled the water and I want that water to be maintained for 8 hours to be as the same. Okay. So nothing but which is helping to make that as a heat energy, which is conducting means which is going to be charge or heat can pass through a material, which is helping that material to maintain. Conductivity is nothing but making that water to be heated. Plain water have taken, I want some heat water. Conduction taken place. Conduction means we're making that to be become a heat. So that water I want to be maintained for 8 hours means thermal conduction is taking place. Got it? Understood? No confusion, right?
No, ma'am.
Ah,
Absolutely.
so plain water I have taken, I want to heat it. Heating is nothing but conduction. To maintain that for certain hours is nothing but thermal conductivity. Means maintaining for so many hours is nothing but now we are thermal water bottles, thermal. Everywhere thermal production is maintained a lot. Okay, because we want that to be maintained for so many of hours. So diffusion of gases. Next is how the diffusion of gases takes place. Let us consider different parts of the gas which have different molecules concentration. It means the density, number of molecules in unit volume is different in different parts of the gas. Let us assume that there is a gas density gradient along z-axis due to the density gradient molecules move to the place of lower concentration from the place where there is a higher concentration of molecules. This process of the mass redistribution will continue till the concentration of the molecules is same everywhere in the container in which gas. Okay. See, for example, if I'm taking a vessel, water molecules, water is there. So once it gets started heated up, how it gets heated up from higher to lower or lower to higher, you tell me.
Lower to higher.
Huh? Yeah. Right? Okay.
Yes.
So next class we will discuss ma because I got a message that out of the time I can't take. So uh, this is about the diffusion of the gases. Okay. So this is your complete kinetic theory of the gases explanation is done. So in next class, next Sunday, I'll take the class. No worries. We will discuss. See, I have explained you in the first class itself about the zeroth law and the thermodynamics also.
Yes.
Okay. So I have
Yes.
explained you reversible and irreversible process also. how this equilibrium takes place also. Thermodynamics process. You just read all this, you'll understand. Okay?
Yes,
Thermal
ma'am.
equilibrium, adiabatic. See, I told you what is adiabatic. Adiabatic is nothing but where it can be pressure, volume, and temperature can be
Very.
varying.
Mm.
Isothermal process is nothing but pressure and volume will be varying, temperature will be constant. Okay, that is what is about this all. Clear? So
Yes.
concept of temperature, very easy. Measurement of temperature, easy. How we are measuring? Different types of thermometers. What are they? Okay, nature of the heat. Normally, how it can be heated. Okay, clear?
Mm. Yes, ma'am.
First law of thermodynamics already discussed in first class itself.
Ah.
Okay,
Mm.
clear?
Yes, ma'am.
So we will go to the next class for the next topic. Reversible and irreversible process. I told you know how this reversible and irreversible process takes place. Reversible means where it can be converted from heat to cold, cold to heat. Irreversible process which cannot be irreversible process cannot be reversed.
Converted. Yes,
Which cannot
yes.
be reversed. Example, you can take the phones. Clear?
Mm.
Mm. Yeah, that's it. You can see it is diagrams, explanation. All about the heat. Means nothing but talking about Carnot theorem is also simple. How this reversible and irreversible process is taking place. You read once, you'll understand. Okay, ma?
Yes, ma'am.
Okay. See you in the next class.
Mm.
So, next topic we will discuss 7 to 12. 1 to 6 units are done now. Okay.
Mm.
Next, we will discuss in the next class 6 to 17. I'll complete your syllabus in the next class.
Okay.
Okay. Prepare well.
Oh,
In the last class, I'll discuss little more. Okay.
okay.
Okay,
Thank
ma.
you.
See you on.
Thank you, ma'am.
Yeah, welcome.
Thank you, ma'am.